All right, so we're going to continue our discussion about exponential functions. Today we're going to be talking about a couple things, mainly natural base exponential functions. But before we get to those, we're going to review something that you learned in Algebra 1, which is when you're given data, how to determine if it's exponential. So we know that data is linear if it has a constant rate of change. So your Algebra 1 teacher said that phrase over and over and over again. So constant rate of change means that the change in y over the change in x is the same for every set of ordered pairs that you could pick. So it's constant. Exponential data doesn't have a constant rate of change because it doesn't have a slope. Right? The change increases as we go on significantly or decreases if we're talking about decay. So what exponential data does have is a constant multiplier. So that means that when you are taking the data and looking at those y values, that you're going to be multiplying by the same value over and over and over again. So in our first example here, we are asked to determine if the data is linear, exponential, or neither. So we're going to be looking for these two things up here. If we determine that the data has a constant rate of change, then we'll say that it's linear. If it has a constant multiplier, we'll say that it's exponential. If it has neither of those two things, then we will say it is neither linear nor exponential. If it is linear exponential, we are expected then to also write the equation. So first thing I want to look at is this table we have in part A. So when I look at these values, you can see that my x's are going up by 1 every time. So when I look at the y values, if it were linear, that would mean that because these values are decreasing, that they would have to be going down by the same amount every time. Here you can see from 12 to 6, I subtracted 6. So minus 6. But when I go from 6 to 3, I'm only subtracting 3. So not linear because that rate of change was not constant. So then I try again and see, okay, could there be a constant multiplier? So when I go from 12 to 6, you're asking yourself, what would I multiply 12 by to get 6? If the numbers are getting smaller, then what you're multiplying should be a fraction. So 12 times 1/2 is what gives me 6. So then I look from 6 to 3, 6 times 1/2 is 3. And so we'll see if it stays constant. 3 times 1/2 would be 1.5. So we have found a constant multiplier. So we will say here that this is exponential because we have a constant multiplier of 1/2. Now, if we know that it's exponential, then that means we need to write its equation. And the way that we do that, first of all, is by taking whatever the constant multiplier is, because you're going to only be writing exponential equations in the form y equals a times b to the x. So we're not going to give you ones that are really difficult where you would have like an h or a k value or anything. The b value is going to be the constant multiplier. And your a value is going to be the y-intercept. So in this case, when I go to write the equation, I have y equals, so a, the y-intercept. When I look at my table, I don't see the y-intercept. However, it should be very easy to get the y-intercept because we should know that at the y-intercept, the x should be 0. So this is really only 1 unit back from the data that I have. So if I count backward to 0, that means that this would also have to have the times 1/2. So if I'm going the opposite direction, it would be multiplying by 2. So this would be 24 because 24 times 1/2 is what gives me 12. So I've worked backwards to see what y is when x is 0, and that gives me my y-intercept. So that gives me 24, and then b to the x, so base is that constant multiplier 1/2, raised to the x power. And so then this is my equation. All right, let's look at b. Again, as I look at this data, my x's are all going up by 1, so I know that those are constant. When I look at my y's, here I added 6. Here I added 6. And here I added 6 again. Remember that you do have to test all. Sometimes they'll try to trick you by making like the first 3 all have the same constant rate of change and the last one having something different. Same with multipliers, so just make sure you're checking all of the data. This one does. All the data that we see shows a constant rate of change, so that means that this one should be linear. And our constant rate of change would be 6/1, which is just 6. And for linear equations, you can write them a bunch of different ways. You could use point slope form if you wanted. I probably, because this is starting at 1, would just do the same thing I did in part A and move backward. So I know that this value plus 6 has to equal 16, which gives me 10. So I've got a y-intercept of 10. Remember that the constant rate of change is your slope. We know that. We typically write just like this is the form for exponential. Y equals mx plus b is the form for linear. So we'd write y equals 6x plus 10. And then we have our equation finished. Okay. So the next part, we're going to be talking about natural base exponential functions. And when we do that, we have to discuss also irrational numbers. So remember, this is review. Irrational numbers are numbers that cannot be written as a fraction of 2 integers. So you can't do like 5/17 or any fraction where we use 2 integers. So in decimal form, we know that irrational numbers never end and never repeat. So irrational numbers that we've already discussed are simplified square roots, so meaning you've broken it down as far as you can, it doesn't go any further, like radical 3. There's nothing else I can do to simplify that. That is an irrational number. We know that pi is also irrational. Today we are learning another number that has a symbol, just like pi. It's the number e, so not the letter e, the number e. When we write it in math, we typically do it with that little script, so it looks like this. So the number e is also an irrational number, and to see its value, I'm going to kind of do 2 things at the same time here, showing you what the value of e is, and also at the same time showing you where to find it on your calculator. So there are 2 places that are going to be important for your e. The first is right above the division key. That's your plain old e. So if we want to know the value of e, I press second, since it's in my blue color, and then I press the division key. That types in an e for me. And then if I press enter, it gives me the value. So it's approximately 2.71. And then obviously you can see, because it doesn't end and it doesn't repeat, we have lots more digits we could write. But this is the number e. Also, if you were wanting to raise e to a specific power, that would be this button, the one that's 2 above the on key. So if I wanted to do e raised to the 5th power, then it already types the e and the gives me the box to put in. And so then we could see what e to the 5th power was. So that is our number e and where to find it on your calculator. We call it the natural base, hence the title of this section being natural base exponential functions, because our new parent function for our transformations in this section is going to be f of x equals e to the x. So we always have, when we do these graphs, a parent pattern. So I want you to realize that this is going to be very similar to our typical exponential, which was -1, 0, 1. And then remember, it was 1 over b, 1b was the exponential pattern. This pattern is going to be exactly the same. It's just that our base on all of these is e. So we have -1, 0, 1, and then we have 1 over e, 1, and e. So it's probably helpful if we write in parentheses the values. Now, we typically use 2.71 like we use 3.14 for pi. However, when we're graphing, you're really not going to get past the tenths place, so we're just going to use 1 decimal place. Now, 1 over e, we do need to know what it is. So 1 divided by, oops, I pressed the times key, that won't work, divided by e, enter, and we get 0.36. So we're going to say about 0.4 if we're rounding to the tenths place. So that makes our parent pattern -1.4, 0, 1, 1, 2.7. So if I graph that, -1.4, that'd be right here, 0, 1, and then 1, 2.7. It does have the same exponential shape that our other exponentials did. It does have a horizontal asymptote on the axis. So just like all the other exponentials, our domain is -infinity to infinity. Our range on the parent, just like the other exponentials, goes from 0 to infinity, not including 0. And we have our asymptote at y equals 0. Now, the way that we transform this is the same as the other exponentials. So we would have y equals, and then we could have an a value. This time it's always e here, and then it's x minus h plus k. So same transformation as in the last set of work that you had. So A controls whether or not there's a reflection, and it also controls our vertical shrink and vertical stretch. H controls horizontal shift, K controls vertical shift. We will not be having B values on these ones. So in example 2, we're going to describe the transformations, then we're going to graph the transformation, list its domain, range, and asymptotes. Sometimes homework problems will ask you to graph the original and the parent. Here I didn't ask you to, since we just graphed it. If graphing the parent on the same coordinate plane helps you, you're always welcome to do that. Just make sure you clearly label which of your graphs is the parent and which is the transformation. All right, so let's look at the transformations first. So here in A, I have this -1/2 out in front of my e to the x. So that means that this is an A value. So A can control two things, reflection and vertical shrink or stretch. In this case, since it is negative, that means that we should, in our transformations, list a reflection in the x-axis. Then the 1/2, since 1/2 is between 0 and 1, so if you go back and look at your 21, 3, and 4 notes or video, we talked about all the transformations again, but that's going to be a vertical shrink. So it's between 0 and 1, so vertical shrink by factor 1/2. And that's all we have. We don't have an h, we don't have a k value. So because we don't have an h or a k, that means we don't have any shifts. So when I set up my little plus sign, it's just going to be on the origin because I have not shifted any. Now I need to write out my parent pattern, -1, 0, 1, 0.4, 1, 2.7. And then I'm going to transform it according to the A, because remember that A values we multiply times our vertical column. So we're going to do times -1/2 on all of these. And so what we end up with, 0.4 times -1/2 gives us -0.2. 1 times -1/2 is -1/2, or -0.5 if you want to write it as a decimal. And then 2.7 times -1/2 is -1.35, so about -1.4. So from our start point, which is the plus sign here, I'm going to go left 1, down 0.2. So left 1, down barely any at all. Then left none, down 1/2, so very small here. And then right 1, down 1.4, so almost to 1.5. And then, because I didn't have any vertical shifting, I know that my asymptote is going to stay here. It always goes through the plus sign. And so then connect with my exponential shape. It says list domain, range, and asymptotes. So my domain is always -infinity to infinity. My range in this case is -infinity to 0 because it's all below the axis. And my asymptote is the same as the parent. It's at y equals 0. All right, last one. Describe the transformations first. So this 2 out in front here, it's not negative, so no reflection. And since 2 is bigger than 1, this is a vertical stretch by a factor of 2. Then this -4, that represents a horizontal shift. And because it's negative, that's moving to the right. So right 4. And then this is a K value, it's positive. So this is a vertical shift, up 1. So do my shifting first. So I go right 4 and up 1. Draw my little plus sign there. This is my start point. This is also where I should be drawing my horizontal asymptote, because you do need to draw it on your graphs. And once I have my start point, then I'm going to write out my parent pattern and make any necessary adjustments. So parent pattern stays the same, but my adjustments change. So in this case now, I'm going to multiply by my A value of 2. So our 0.4 times 2 is going to give us 0.8. 1 times 2 is 2. And then 2.7 times 2 gives us 5.4. So that means I'm going to, from my little plus sign mark here, go left 1 and up 0.8. So left 1, up 0.8. Then left none, up 2. 1, 2. And then right 1, up 5.4. Right 1, up 1, 2, 3, 4, 5.4. And then I'm going to connect this with my exponential shape. And then to finish it off, I've got my domain, range, and asymptotes to list. So domain, I've set on your exponentials as always, -infinity to infinity. The range on this one starts at the asymptote and goes up, so 1 to infinity. Remember, that should correspond with your vertical shift. And then my asymptote is y equals 1. All right, rewind if you feel like you need to hear anything again. Otherwise, you should be set to go on to your homework.